I am going to present my papers according to the application. Uh, the first application I'm going to present about retinopathy detection and grading. The retinopathy problem or the retinopathy disease appear in retinal images for diabetic patients. Diabetic patient may lose his sight if not detected and medicated early. So it is very, very important problem facing doctors working in that field. I would like to present computer-aided diagnosis system for detecting that disease, for detecting lesions in the images to be easier for the doctors to deal with later on, or to help him to take his decision. Unfortunately, detection on and degrading of DR are difficult. It is really my expertise in medical images. I found that these images are very, very difficult for analysis and for detecting lesions. These images usually suffer from unsaturation and noise because most of the images in the benchmark databases taken by different camera and different environment, so it is with different brightness, with different maybe suffering from unfocus, sometimes noises. So it is considered a very difficult task. The first research in that field in article number 6. In this research, we aim to detect lesions like hemorrhage, exudates, and also detecting vessels, because the vessels also could be a sign of a problem in case of number of vessels is very large or dilated. Exudates also a problem. It is a leakage of protein under retina. Hemorrhages are the leakage of blood from the blood vessels. Also detecting the vessels to detect if it is dilated or not. Dilated because of blocking some vessels in the images. So some blocking of the vessels in the retina, and decide if we have a problem or not. This first paper is concerning segmentation to detect lesions, exudates, hemorrhage, vessels. Also, we detect vessels. We detecting disc of optic disc, and to detect all the components of the retinal image. This is my proposed method for segmentation, for segmenting the lesions. The phone's image channels Y, CB, CR. We separated into the image into channels, and we apply on the brightness Y gray world correction algorithm. Then rebuild YCBCR is converted to red, green, blue, and applying contrast limited adaptive histogram equalization on the resulted image, G image, green channel image, and then applying thresholding and morphology operation, and then ending with the previous result to produce image with hemorrhage and mucola. Then minus the image resulted from the previous stage after applying morphology operations, and then it gives me the hard exudates. Then we can add in the result of hard hemorrhages with the resulted image, VHM, which contains the vessels, hemorrhage, and microaneurysm added together minus the resulted from the morphology operation here to resolve the visit. Anyway, as shown in this diagram, we could extract most or all the lesions, optic disc, exudates, hard hemorrhages, vessels, macula, and microaneurysm. It successfully extract most of the pixels affected by one of the lesions of the DR. This slide shows the results of using proposed pre-processing method using contrast limited adaptive histogram equalization and unsharp filter to produce the images like this. I build the image in color to show the result clearly. And then, as shown on the previous slide, we applied some operations on the green channel. The down, the bottom, on the right bottom of the slide shows the extraction of microaneurysm and the hemorrhages and the vessels, and going down shows the extracted exudates and how we could remove the optic disc. As shown here, the extracted vessels successfully extracted, and as shown in the lower row, I colored the image according which is the lesion and surrounding the optic disc to show that it has been extracted, and the color in blue meaning that there is an oxidates. The colors in green, it shows the detection of hemorrhages. As I said, I count all the pixels of each lesions and consider the number of pixels as a feature. Applying the supported vector machine, it gives me about 94% nearly for sensitivity. Sensitivity is the most our concern, because sensitivity it conveys the number of people which has the problem of retinopathy. So it is considered good and encourage us to continue on that field. Brightness correction using real-world and image histogram pre-processing like CLAHE method and contrast stretching function and pre-processing helps us. All these methods or techniques of image processing helps us to detect the lesions easier. Sensitivity is considered good, but still we need to get better results. So that's what we are going to do in next three papers, next two papers. Article number 7, we are going to use our proposed CNN model to classify the diabetic retinopathy into normal and abnormal, and also to grade the DR into 5 grades. This paper proposes enhancement process as we explained in the previous paper, and proposes two architectures, one for classification into normal and abnormal, and the other one for classifying the grades of the DR. And also we're going to use the pre-trained models to test them if they are suitable for our application or not. In this slide, we show the samples. We show samples from two different databases. The first one is Mesidor 2, and the second one Kaggle iBasis database. The first one, Mesidor, is 1,745 fonts images, and from Kaggle 3,191 images. The pre-processing method is presented here. Pre-processing is using histogram match. This is a new proposal. We are proposing to fix the quality of the images under processing by selecting one of the images which you considered as good image and in good state and good quality, and then using the channel red and blue for comparison with every image in the database during processing before training. We rebuild the database again after correcting the brightness using this pre-processing method. Comparing the red and blue image with a reference image red and blue, and then applying a median filter on all the images, the corrected red and the corrected blue and the original green. Applying them contrast limited adaptive histogram equalization, and then unsharp filter as explained before. Then removing all the black corners to be like this on the right of the slide. First, using pre-trained CNN models for classification, I inserted last layer because I have just 5 classes. Most of the pre-trained models, like AlexNet or GoogleNet, are ES50Net. These 3 models classifies input into 1,000 classes. I just need just 5 classes, so I inserted that layer, a new classification layer, to make the model classifies the images into 5 classes. The results of pre-trained models as shown here. And I use that models for training my images from scratch, not just for classification. Now I trained them, and then dividing the image into 2 sets, set for training and set for classification. Not used before by the model. It is the first time to see when I am testing. To test its ability to classify the image into grades. AlexNet, GoogleNet, RES50Net around 74%, which I'm not happy with, so I have to decide to find another solution. I thought if using the pre-trained model, not for classification, just for feature extraction. I used for feature extraction as shown here. I get the weights of the layer before the last layer, which is 1,000 values I considered as features, applying the image and extracting features from that layer, and input for classification in supported machine. Unfortunately, the results still not good. I expect that because the images, as I said before, the images are difficult, suffering from many problems. It is not easy to detect retinopathy using models originally built for classifying something else. That is my point of view. These pre-trained models for classification of mouses, pens, keyboard, screen, dog, something like that. It's not suitable for medical images, which the relation between the pixels is very important and conveys the disease. The relation between pixels is just very close lesion. It's not like other images. That's my point of view. These pre-trained models are not suitable for medical images. This is my expertise in that field, or to be more specific, not suitable for fonts images. This is my proposed CNN model, 17 layers. I would like to mention about the size of the filter, which is more suitable for fonts images. I used a small, very small size 3 by 3 to be suitable for the lesions like microaneurysm. The results are considered good. I used two types of split ratio, 70 to 30, 70 for training, 30% for testing, 80 for training, 20% for testing. The result is considered good, and as shown the procedure 1, 93% F1 score, 91 for procedure 2, 91 for Kegel, and we think the results competing most of the results in the literature survey. Here we display the confusion matrix using the two split ratios, 70-30 and 80-20. We focus on 70-30 because this is the default by most of the researchers. For Mesidor 1, sensitivity 85. For Mesidor 2, sensitivity 91. For Kegel result from AI basis as 90%. These are the results of grading. It is considered good also, competing the others. F1 score is 87 for Mesidor 1. F1 score is 88 for Mesidor 2, and for Kegel it is comparing with others. We will find that our proposal has got better results. We can conclude that the results stands in a very good position among other leading studies. I cannot say that it is the best, but it stands in a very good position among other leading studies carried out on the same databases. The two models outperform the pre-trained models. Also, that using pre-trained models was not successful in extracting features or for classification for fonts images. It may be successful in other applications, but in this application is not successful. Classifying the severity of DR till the time of that paper needs more research to obtain better. This is a paper published a few months ago. We have to do more effort, especially in classifying the severity of DR. Pre-processing techniques for enhancing the image raised the accuracy by 10% and AUC by 13%. Now we're going to describe the last paper in that field. It is published uh, 3 months ago. This paper, I have a contribution to go back to what have the people were doing before, the extracting features and submitting the features to a CNN model for classification, not just taking the image and making some enhancement and feeding the machine learning, whatever CNN to classify. No, but I have to extract feature because I am my point of view is that extracting feature, we detecting the lesions, and then we can the classification will be better, and we can use also the CNN or any machine learning algorithms for classifying the features, not classifying the images. This is my pre-processing method in this paper. There is a difference from other paper of segmentation I discussed before. I'm using it only on a green channel, not like on red and blue as before, and using the same correction algorithms. The results considered good. All the lesions clearer than the original image. This is my contribution in this paper. Applying the pre-processing technique we proposed before on the green channel, dividing it into blocks or sub-images, applying the local binary pattern on each block to calculate the extracted features, concatenating all the features in one vector. Then I proposed to use run length encoding for zeros. All zeros are replaced by a number representing its numbers, a number of zeros. Like here in the shown on the right, the number of zeros here represented as 9, number of zeros here represented as 10, and then concatenating the numbers, reducing the feature vector into 3.5% of the original one. After that, we cannot use the original equation to calculate the number of coefficients, as shown b multiplied by b minus 1 plus 3. Now we have to use the proposed block on the right. When using radius 2 and block size 5 by 5 and the division 10 by 10, we should use the features size will be 16,150, and so on. And as shown, we can, if we use the 5 as a radius, and the block size will be 11 by 11, and the division will be 45 by 45. This value is dependent on the original image because we resized it into fixed size, so we got that values. These values we used for extracting the features, and now we have a limited number of features we can process. After calculating the features using uniform local binary pattern encoded 0 algorithm, which we proposed, and then applying normalization and also contrast limited adaptive histogram equalization on the resulted image, we reform the vector into image, square image, and applying contrast limited adaptive histogram equalization on that image, and then we create another database of feature of images contains features of local binary pattern encoded 0. The proposed CNN for classifying ULBBEZ algorithm shown as shown 17 layers but as shown, we used very small filter size, 5 by 1. 5 by 1. Why we use 5 by 1? Because as we concatenating the features and to build the image, the features, the extracted features, dependent on its neighbor. If we making the filter size 2 dimension, it will cover two features not related to each other. So that's the reason why you're using 5 by 1 filter size. We tested which is the best for classifier support vector machine, which is the best kernel, using our method at neighbors 20 and radius 3, just for testing which is the best kernel. We found that the linear kernel is the best for support vector machine classifier, and also we found that the radius 3 is best when applied on Messenger 2, as shown in the image. The radius 3 is the best. The kernel function linear is the best. Trying to find which is the best neighbors, we decided that the radius 3 is the best. Which is the best neighbor? Comparing different neighbors results, when using different neighbors, the results using support vector machine or CNN model, we found that for Messenger 2 that the neighbors number 20 and the radius 3 is the best. For Kaggle I-classes database, we found two pairs are the best, competing each other. The number of neighbors 20 and 3 or 24 and 3. These are the confusion matrix for results shown on the table. Of course, these are samples. These are samples of our results, the best samples we got. In the case of grading classes of retinopathy, as shown here for Messenger 2 at pair 24.3, it shows if score 95, and in case of I passes database 24 and 3, we got 93 for one score. In case of support vector machine on using the same pairs, the best in Messenger 2, 83 of score. In case of support vector machine using benchmark database iPasses at the same pairs, we got 89. Comparing the two rows, the first row for CNN, the second row for support vector machine, we can conclude that our proposed model for CNN is better than support vector machine because it gives better results in general. It has like here, for example, 95. Here is 83. The difference is too much. Still, the results of classification into grades, classification of grades of DR is not good, especially for class number 4. So many researchers have the same problems. they proposed to regroup the classes into different groups. For example, one researcher regrouped 1 and 2 in one class and 3 and 4 in one class, and sometimes other researchers using another grouping. Anyway, I proposed this grouping just as the first one, 0, no the DR, no diabetic retinopathy. 1 is mild, it's okay. Grade 5, I proposed to conclude the severe classes. Second, let's say class number 2, class number 2 moderate, and 3 severe NBDR and proliferative NDR. As I mentioned before, severe is case, but 4 is a dangerous class. That means the patient is in the near future will suffer from losing his sight. To find the best pair of neighbors, B and R radius, as we decided in the previous slide, that the radius 3 is the best. So we concern here the neighbors. We found that in Messenger 2, neighbors 24 is good, and also in Kegel 24 is good. And the results we obtained is promising, and it is it is superior on other literatures, and gives us a good result. For example, and as shown here for Kegel, we got F score for support vector machine, F score 92, for CNN 96. As explained before, CNN, our proposed model is better, and for Messenger 2, we got for support vector machine 90 for F1 score, and for CNN, our proposed model, we got 98, which is very, very good. That these results is better than others till now on from the literature. Good, considered good. It could be used for other fields of medical images to classify the diseases on detecting lesions. I think it is promising approach if it is applied on easier data basis of medical images. And as explained, we can conclude that the proposed CNN model performs better than supported vector machine for classifying features of the extracted features, or our extracted features. As our method is superior to other methods, as revealed by its small feature vector. That is very, very good achievement, reducing the number of features to 3.5% of the original vector size. That is considered good. Regrouping the DR grades into new grades gives us a solution, but it's still not the final solution.